Hello everyone. So today I will solve this problem 2.2 of Pathria. So let's read the question. Verify explicitly the invariance of the volume element d omega of the phase space of a single particle under transformation from the Cartesian coordinate to the spherical polar coordinate. So as you seen in my previous video, I have solved and showed that the volume element d omega will be same for any canonical transformation. We also know that the Cartesian to spherical transformation is also canonical, but we'll show it explicitly. Okay, let's go to the solution. So to show the invariance of phase space volume element under transformation from Cartesian to spherical, we have to show the volume element multiplication of dq and dp. This should be invariant. In my previous video, I have also used Jacobian. In this video, I will also use Jacobian to solve this problem. Actually, we have to show that the Jacobian determinant that should be unit, so that this volume can be same. Our goal is to show that. So this is our goal. We have to show the multiplication of the dqy and dpi. This should be same for a single particle. So this is our Jacobian determinant. So these two quantity we have to find, and after finding these two quantity, we put in this equation, and we will check that the Jacobian determinant is 1 or no. So I have also attached some PDFs in my Telegram group. I think you should read about the Jacobian, why I am using that, what's its physical significance. I think you should read it. I have also provided those PDF in details. I think you should read, and these things are very clear, not very difficult. Okay, let's go. So we know the relation between units in Cartesian and spherical. So these are the relation we all know: x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta. And from classical mechanics, we have solved the Hamilton's equation of motion. From that, we can write for Cartesian coordinate as well as for spherical coordinate, because the Hamilton's equation of motion is the general one. So from that we can generate any sets like Cartesian, cylindrical, spherical, which we want. Now we know the Lagrangian. This is basically t minus b, and here assume that b, this is only function of position, not the function of velocities. So now we can write the kinetic energy as like that, and the potential energy. By the way, this potential energy will not contribute when we calculate the momentum, because all are derivative of the Lagrangian with respect to their velocity component, so it will cancel out. So after a few steps, you will get this equation, and from that you can calculate PR, P theta, and also P phi. So these are the sets of equation. Now we have to find the Jacobian determinant element. So our first element is that. So this is basically the inverse which we written in the determinant there. So this del xyz by del r theta phi, this is basically that. So we have the equation, sets of equation. From the equation we can calculate del x by del r, del x by del theta, and also the other component. So after calculating this, you will get this type of determinant, and if you solve it, you will get the result is r square sine theta. So this thing is done, and equation 4, this will as in equation 4 we have written in the form of del r theta phi by del xyz. So we have basically inverse the result. Now we have to find this element for the momentum also. So we have to find that, but there for the position coordinate we have the relations, but for the momentum we have no relation. So we have to establish the relation. So first try with px. So we can write px at mx dot, and from the x equal to r sine theta cos phi, we can calculate x dot, and we have to put that here. After simplification, we will get this type of result. Similarly, for py and pz, we will obtain this type of equation. So everything is now ready. Now we can calculate it easily. Now make the determinant. So this is the determinant, and from the relation we can calculate each element here. So these are the elements, and if you solve it, you will get this relation. And in the determinant we have to solve that. So this is our equation 6, and the previous result was in equation 4. So both we have to put in equation 1. So we have put it, and basically it gives us 1. So we have proved that the volume element is also conserved here, because it's also a canonical transformation. I think it's clear for everyone. If you have any doubt, you can comment me, and also text me my mail, or my Telegram ID is also provided. Thank you.